So beta and gamma function. Beta and gamma function. So last time we discussed about Euler and this is SRN. Constant. Okay. So we also arrive at the conclusion. This constant, this is your gamma, and finally we arrive at the conclusion. This is gamma is here, and this gamma defined as limit n tends to infinity Hn minus log n, where this Hn given by 1 upon k, and this k equal to 1 to n. So basically, if you see, this is a harmonic series. This is a harmonic series. And we have to prove for this is value of this gamma lies between 0 and 1. 0 and 1. So last time we discussed about the behavior of this function. That means behavior of this function, that is by taking this is a n plus 1 and a n, which is equal to summation is this. This is your k equal to 1 to n, 1 to infinity. Sorry, this was infinity. K equal to 1 to n, or we can write n tends to infinity. No problem for this. And here, this is the 1 of k plus 1, and this is your n plus 1 is this, and this is raised to power k plus 1, and value of this less than c. Okay? So that is a negative, and where this an, so an we consider like this at n minus log n. Okay. So finally we get this value. So it means this is negative. So it means this is your negative value. Negative value means if this is negative value, that is decreasing function. So finally it is decreasing function. So we can say this is your decreasing one. That is the decreasing one. Okay. If we take suppose 1 upon t, for example. So So it means this is given decreasing. So if we take 1 upon t, 1 upon t, if we take 1 upon t, why? Because the t is here, when value of t increase, then 1 upon t will be decreased. So 1 upon t is, this is value of t, where that is a decreasing function. That is a decreasing as t increases. Okay, it decreases when decreasing when t is increasing. When t is increasing. When t is increasing. So we can write now here value this. So 1 upon k less than, if we take it, this is k minus 1 to k, and this is your dt over t. So this is the value of this. This is less than 1 upon k minus 1. K minus 1, here we can take k, this value of the k, greater than equal to 2. Clear? Equal to 2. So equal to 2. So it means this is our integration, k minus 1 to k, and 1 upon k. 1 upon k. What is 1 upon k? 1 upon k. So and this is starting from k equal to 2 here. So it means 1 upon 2 plus 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5, 1 upon 6. So it means adding 1 and subtracting 1. So when we add, so this becomes your Hn. That becomes your Hn. Hn means, as we consider here Hn. So this is Hn. Hn is this. So this is our Hn. That is given by this. This is your Hn is this. And this is your Hn. And here you will get this value. So this is here. So 1 upon k minus 1. So that becomes this Hn minus 1, because this series goes up to 2 is here. So 2 to 1 upon 2 minus 1, 1. So 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5. This goes up to n minus 1. This goes up to n minus 1. So finally this becomes your Hn minus 1. So so here we can write now, so which implies, so value this one, that becomes your Hn. This is minus 1 less than, so starting from 2, so 2 minus 1, this is a 1, this is 2, so this is your dt over t. Now this is 2, this is 3, dt upon 3, this is 3, this is your 4, dt upon 4, sorry, dt upon t. Dt upon t plus this goes up to n minus 1. This is your n. So we can write that dt upon t is this. So this is less than at n minus 1. At n minus 1. Okay? But this is your due to this one. 1 upon k minus 1. So this is less than h minus 1. Or finally, this becomes, so if it h and this minus 1 is this. So what is value of this? This is less than Value of this. This is log n. And here you can write now as n minus 1. At n minus 1. So it means which implies hn is this, minus 1 is this is your log n, this is your log n is this, and this is your n minus 1 is this. So we can write now this minus 1 is here less than minus 1 is this, and here minus hn plus log n. This is less than minus 1 upon n, or we can say value of this becomes 1 greater than an, and this is greater than 1 upon n, due to this is due to here. So given by this. So finally we can claim the value it means which implies an. So this an when n tends to greater than 0. So it means this 1 upon n is here. So finally we can say this is finally we can say this an, this is an is non-negative value. Non-negative value, but less than 1. But less than 1. Clear? So this is the value of this Euler constant. So it will Euler constant lies between 0 and 1. But it will always less than 1. Next now, gamma function. The gamma function. Gamma function. So I think till now we studied gamma function by taking some numerical value gamma n, gamma 2, or the gamma n where n is 1, 2, 3, 4, 5, whatever like this. But here we will define gamma function in different manner. And this definition was given by Weierstrass. Defined gamma function. So basically, this is the concept of Weierstrass, or we can say this is concept of the Weierstrass, who was a great German mathematician, define gamma function as this is 1 upon gamma z equal to z is this, and e raised to power This is the gamma and this is your Z. That is infinite product n equal to 1 to infinity, and this can be written as 1 plus Z upon n, and this exponential of minus Z upon n. That is the definition of the gamma function. Definition of the gamma function. So here, this gamma, that is your Euler constant. This is your Euler constant. And this is most important. This is basically uniform convergent. This is uniform convergence, closed region in Z plane. In Z plane. And further, this function defined as a gamma. This is gamma function defined by the sign of the integration. That is gamma z. So gamma z given by 0 to infinity is this. 0 to infinity e raised to power minus t and t raised to power z minus 1. This is your dt. So here, real z that must be greater than 0. So here we're talking about this. And this is a well-known definition, and all of you are familiar with this. This is also known as the Euler integral. Euler integral of the second form. Or Euler integral. Euler's integral of the second kind. A lot of the work done by Euler, done by Euler, and many properties of the gamma functions and beta function given by the Eulers. And here, what is property of this Weierstrass integral? So first, we would like to take this one, this condition. So this one, that is your. This is a Weierstrass gamma function. This is Weierstrass gamma function. And property of this gamma function. So first, this is analytic with all finite value of this. Properties. Number one, gamma z. Gamma z analytic. Analytic for all finite value of z. So now it means finite value. Finite value means, so here we can take all or we can say this is or you can write now here. This is the analytic accept non-positive integer. Positive integer and z equal to infinity. So this define only for the positive value. And second one is it has simple pole this part simple pole is non-positive integer. Simple pole at z, that is non-positive integer. Non-positive integer, and then this is a 0. This is sorry, 0 is this 0 minus 1 no, minus 2 minus 3 minus 4 so on. Essential similarity at point z equal to infinity. The most important essential similarity z equal to infinity. Fourth one, gamma z is never 0. Gamma z is never 0. इसका मतलब है गामा z का जो वैल्यू है that cannot be equal to 0. Why? Since 1 upon gamma z does not have any pool. Does not have any pool. Yeah. Does not have any pool. So, this is equation. Suppose this is equation number 1. If I take this is equation number 1. Now, now taking the log of each member or the both the side, taking the log of 1 log 1. This gives to you This is log gamma z equal to minus log z, and this is a minus gamma z is this. This is the gamma z. This is gamma z, and here value of this all will become in the form of the summation. So this can be written as 1 plus z upon n, and here we can say z upon n is this. So here logarithm is this. So we can write like this. See, come on this side. If this is product form, this is the product form. So as you know, simple the formula is this. As you know, this is that is as log m into n equal to log m plus log n. Okay. Now on differentiating, then on the differentiating both the side, differentiating to both sides, to both the side, we get value of this. So that can be written as gamma dash z. This is gamma z. This is equal to minus 1 upon z. Clear? This is log z is this. Log z is this. So this is log z. So log z equal to 1 upon z minus 1 upon z. And here again differentiate with respect to z. So you will get this is equal to gamma. And minus is this. And here we can write now. This is n equal to 1 to infinity. And this becomes 1 upon z plus n. And here we can write now this is minus is this. Yeah, this minus n. And here we can write now this is equal to 1 upon n. 1 upon n. Okay. So this is so we have to differentiate this. So ultimately when we have to differentiate this, so we can write now this log 1 plus z, it means n plus z divided by n. So when differentiating, so this becomes 1 upon n plus z divided by n. And here we are having minus z means so with respect to z. So you will get minus 1. So finally this is 1 upon n is there. 1 upon n is this. This can be written 1 upon n. Or we can write now this is or we can write this becomes gamma dash z upon gamma z equal to minus gamma and minus 1 upon z minus 1 upon z, and this is your plus is this, and here we can start now n equal to 1 to infinity, and this is now z is this, and here we can write now this becomes n z is this, and there n is LCM to n is this. So this is given with this. Okay, so value of this. Given by this. Now we can check whether it's conversion and divergent. Conversion and divergent. So basically, if you see, this your summation is this. Multiply this, so here you get z upon z plus 1 upon this n square is this. So this is from this. So finally, this gives just like this is summation is this 1 upon n square. 1 upon n square is this, and starting from n equal to 1 to infinity. So finally, your series become 1 upon 1 square plus 1 upon 2 square, 1 upon 3 square, 1 upon 4 square. So this is your conversion. This is conversion. So hence this series is conversion. So this is simple. So this is the conversion. So someone can ask this series conversion and diversion under this rule. So this is the rule. Simple taking summation of this. Okay. So finally, this is the conversion. So now, given by this, on putting, and so this, so we can write this is number 2. On putting, z equal to 1 in 1. So we get 1 upon gamma 1 equal to e raised to power gamma. This is the product, and this is n equal to 1 to infinity. So 1 plus 1 upon n minus 1 upon n. Okay. So this can be written as value of this. So m1 plus here. If you see, so here you will get the product of this. So it means n plus 1 upon n. So basically this one. So this one can be written as n plus 1 divided by n, and this is your exponential of minus 1 upon n. Exponential of minus 1 upon n. So when you put now n equal to 1 to infinity, so ultimately what you will get, suppose n equal to 1 to infinity, so it means 1. So 1 plus 1 divided by 1 into, again, so here you will get now here value of this becomes n equal to 2. So this is your 3. 3 upon 2. Next is 4 upon 3, like this. So it means 2 is this is cancel out. 3 is this will cancel out. Next you will get 5 upon 4, this is cancel out. Okay. Then you will get 6 upon 5, this is cancel out. Cancel out. So finally you will get this. That is the last term. So last term of this now here. So that becomes the value of this. So it means so it means here this n is here. So it means here we can write now limit n tends to infinity, and you can say n plus 1. Okay, n plus 1, and this will convert into hn. This will convert into hn. So this is the exponential is this. So here we can write now exponential of Hn. This is exponential of minus Hn. Minus n. So finally, e raised to power gamma is this. Limit n tends to infinity. And here we can write down n plus 1. And value of this Hn, now putting the value of Hn, so this exponential of this minus gamma, and this is minus log n. So basically in your book, they have written here, this is a minus epsilon. So basically epsilon n is this, so epsilon n tends to 0, this is two-minded value. Two-minded value, this x tends to h tends to infinity. So that is ultimately meaningless, so I will not put it here. This one. So finally you will get, this is your 1 upon gamma 1 is this. And here this is your e raised to power gamma. And this value of this now, so gamma is this, and this is your log n is here. This is your log n is this. Log n is this. So finally, we arrive to value of this. So it means limit n tends to infinity. And here we can write n plus 1 upon n. And because this exponential is this, so exponential this and log is this. So finally, this log will cancel out. So finally, you will get a minus n. So minus n plus 1 here. So this is the exponential of this minus ultimately this come in the denominator. So and here we can write now minus gamma is this. So this is and this is the cancel out when you put the limit. So that gives equal to 1. So hence we can say, which implies gamma 1 equal to gamma 1. Okay. So now putting the value of gamma 1 in equation number 2. On putting this equation number 2. So this is the value of on putting the value z equal to 1 and gamma 1 equal to 1 into to 2. So this gives gamma dash 1 upon gamma 1 equal to minus gamma minus 1 plus summation this n equal to 1 to infinity, and here z equal to 1, so z equal to 1 is this, and here we can write now n is this, n plus 1 is here, okay, n plus 1 is this. So this can be written as minus gamma minus 1, and this becomes plus summation n equal to 1 to infinity, and here you will get 1 upon n minus 1 upon n plus 1. Can we write? So this one, okay, n plus 1 is this. Go for the summation. So summation means 1 upon 2. When I go for summation, so 1 upon 1 minus 1 upon 2. Clear? Then plus 1 upon 2 minus 1 upon 3. So this will cancel out. Then here you get 1 upon 4. So on. So ultimately, sometimes it will cancel out and you will get this term 1 upon 1. So it means this can also be written as minus gamma minus 1 is this plus limit n tends to infinity 1 minus 1 plus 1 upon n. So when put the limit, so this becomes 0. Okay, and this is also known as the telescopic series, also called telescopic. Series. Okay, so finally we get to this equal to this. Clear? Any doubt? Then you can ask now. Any doubt? You can ask. Anybody else? Okay, so there is no doubt. Okay. Have a great day.